Hello, welcome to my video presentation on coloring. To start, we have vertex coloring, which is given that graph G a coloring of the vertices. And then there's multiple ways that we could do this. One such way that we will be talking more about is what it means to color properly. And so the term proper refers to the property of a graph's adjacent vertices being colored differently. This then leads us to the chromatic number, which is the smallest number of colors needed to get a proper vertex coloring. And we can express it in this notation here, which we'll see throughout the rest of this worksheet. The first theorem that we'll be going over is the four-color theorem. And this states that if G is a planar graph, then the chromatic number of G is less than or equal to 4. So now onto example number 1. Example 1 says to draw a graph with chromatic number 6. In other words, a graph which requires 6 different colors to properly color the vertices. So one such graph that would satisfy this would be the K6 graph. So we see in this graph here that each vertex is adjacent to all the other vertices. And so therefore, to properly color this, it would look something like this. So then the next part of this question is, could your graph be planar? Explain. Even if we had chosen a different graph with a chromatic number of 6, it still could not be planar. As given by the four-color theorem, any planar graph will have a chromatic number that is less than or equal to 4, and our chromatic number here was given to be 6, therefore it cannot be planar. So now on to a couple more definitions and theorems. So a clique is defined as a set of vertices, all of which are pairwise adjacent. So in other words, a clique of size n is equal to the complete graph of Kn. And then so the clique number is the largest n for which the graph contains a clique of size n. And this brings us to our next theorem, which states that the chromatic number of a graph G is at least the clique number of G. So for non-planar graphs, in which case the four-color theorem does not apply, this can help us form the lower bound of possible chromatic number chromatic number values that our graph could have. And then with Brooks' theorem, we can get that any graph G satisfies the chromatic number is less than or equal to the largest degree of any vertex in G, written symbolically here, unless G is a complete graph or an odd cycle, in which case the chromatic number is equal to the largest degree of any vertex plus 1. So from Brooks' theorem, we were able to form the upper bound of possible chromatic number values for non-planar graphs. And also in the second half here, you see that if we're given a complete graph or an odd cycle, then we can actually figure out what the chromatic number is pretty easily. So now on to example number 2. It says to find the chromatic number of each of the following graphs. So to start with this first one here, we know that by Brooks' theorem, the chromatic number is less than or equal to 3. As we can see here, this vertex is adjacent to 3 other vertices. Write it as this. Then the largest clique size here is 2, simply because we have an edge. So therefore we know that our range for the chromatic number is that the chromatic number for this graph is greater than or equal to 2 and less than or equal to 3. Alrighty, we can take some colors. If we start at the vertex with the greatest degree, so either this one or this one, I'm just going to start over here, and I'm going to designate that as blue. Connecting off of it, we know that this one can be green, and it is not connected to this vertex in the middle here, and that's connected to blue, so it cannot be blue, but it can be green as well. Same with this bottom one here. Then for this final remaining vertex, we know that it cannot be the color green since it's connected to 3 different greens. However, it is not connected to a blue colored vertex, so this could also be blue, giving us the smallest amount of colors used. And so the chromatic number is equal to 2 in this case. Alrighty, moving on to the next graph here, we have a cycle with 7 vertices. As given in Brooks' theorem, we know that for any odd cycles, the chromatic number is equal to the largest degree of any vertex plus 1. And the largest degree of the vertices here is 2. Therefore, we know that the chromatic number is equal to 2 plus 1, which is 3. And we can show that here by starting with 1 point. It's connected to 2 other points that are not adjacent to each other, so they can both be deemed as the color green. Now each of these points, or the next vertices connected to green, are not adjacent to any blues, so they could also be blue. And then this leaves us with 2 adjacent points that are uncolored. Either one we can pick to be the color green. However, for this last point here, it cannot be blue since it is adjacent to a blue, and it can't be green since it's adjacent to green. So we need a third color. Moving on to the third graph. This graph is planar as there are no crossing over of edges. So therefore we can use the four colors theorem, in which that means that the chromatic number is less than or equal to 4. We also know, looking at this graph, that the largest click size is 3, which gives us a lower bound. And so therefore we can say that the chromatic number is greater than or equal to 3 and less than or equal to 4. If we get started on this, starting with the vertex of the greatest degree, that would be the one here in the middle. And then if we looked at, to start with one click, say this triangle here, we would need 3 different colors. We have blue, so then one vertex can be green, the other pink, and then if we move on to the next click, we have blue, pink, and an uncolored one. So that can be green. Again, moving down to the next click, we have blue, green. So this third one must be pink. And that leaves us with this last vertex, which is connected, is adjacent to a green vertex, a blue vertex, and a pink vertex. Therefore, to make this proper, we need to use a fourth color. And therefore, the chromatic number is equal to 4. For this fourth graph here, this graph is the complete graph K5. So given in Brooks' theorem, we know that for complete graphs, the chromatic number needs to equal the largest degree of any vertex plus 1. And so the largest degree is 4 plus 1 equals to 5. So we need to use 5 different colors in order to properly color this graph. And it would look something like that. On to the last graph here. We know by Brooks' theorem that any graph G that is not complete or an odd cycle has a chromatic number that is less than or equal to the largest degree of any vertex. So therefore we know that the chromatic number is at most 3. And then we see here that the largest click size is 2. So therefore we know that the range in which the chromatic number could occur is the chromatic number greater than or equal to 2 and less than or equal to 3. So I started coloring by working with the inside. I decided this one to be blue. And then it is connected to 3 other vertices. So this one can be green. This vertice is not adjacent to that one, therefore it can also be green. And this other vertice here is not connected to either of the green vertices, therefore it can also be designated as green. Then moving to a different vertex, if we move down to this one here, we know that it's connected to one that is uncolored as of now, and 2 that are uncolored actually, and a green one. So therefore this vertex cannot be green, but it can be blue since it is not connected to this blue vertex. So that gives us there. This vertex up top cannot be blue. It is adjacent to a blue vertex, and it's also adjacent to a green vertex, so therefore it can be neither blue nor green, and so we have to use a third color, pink. A similar situation occurs when we go down to this vertex here, which is adjacent to a green and a blue. This one must also be pink. And moving along, we have a vertex that's adjacent to a pink one and a green one, therefore it must be blue. This vertex here is adjacent to a blue vertex and a green vertex, therefore it must be pink. This vertex up top is adjacent to 2 pink vertices and 1 green vertex, therefore it must be blue. And we know that the chromatic number for this graph is equal to 3. Alrighty, so we have the chromatic index, which is defined as the smallest number of colors required to properly color the edges of a graph G, also expressed symbolically here. And then this leaves us to Ising's theorem, in which he states for any graph G, the chromatic index is either the largest degree of any vertex or the largest degree of any vertex plus 1. And so breaking down this even further, we can classify graphs as satisfying the chromatic index equal to the largest degree of any given vertex in a graph as class 1. And so class 1 graphs include all bipartite graphs and all planar graphs satisfying the largest degree greater than or equal to 7. This does not mean that other graphs cannot be included in class 1, but these are ones that are always included. And then so graphs satisfying the chromatic index equal to the largest degree of any one vertex plus 1 are known as class 2. And so on to example 3. It says, suppose we want to schedule some exams for CS courses with the following course numbers: 1007, 3137, 3157, 3203, 3261, 4115, 4118, and 4156. Now suppose also that there are no students in common taking the following pairs of courses, as listed here. And we want to know how many exam slots are necessary to schedule the exams. So the first step would be assign each of these course numbers as vertices. Like slow. And now we are going to want to connect or form an edge between any vertices that have students in common. So I already did this ahead of time, but it will end up looking like the following. Alrighty. So it ends up looking like this. And so we know by Brooks' theorem that the chromatic number is going to be less than or equal to the largest degree of any vertex. So therefore we know that chromatic number is less than or equal to 5. As we can see here with 4118, it has the largest degree of any vertex. It has 5 edges coming off of it. And then we also can see that the largest click size in this graph is 3. You can form some triangles in here. So therefore, we know that the chromatic number is greater than or equal to 3 and less than or equal to 5. So we'll need at least 3 colors for this. Starting with the vertex of the greatest degree, we can assign that the color blue. Then from here we see that 4156, 4115, and 4118 form a click. Therefore, the 3 of them need to each be a different color. So then we can move on to another click here. We see that 4156, 4118, and 3203 form a click. We already have 2 colors assigned, so therefore it cannot be blue and it cannot be pink, so it must be green. From here we can also get a click from 4118, 3203, 3157, and since it's adjacent to both the blue vertex and a green vertex, this one must be pink. The vertex 3261 is adjacent to both a blue vertex and 2 pink vertices. Therefore, it must be green. (3137) is only adjacent to 3203, which is green. Therefore, it could be pink or blue, either one. I'm going to choose pink. And then 1007 is not adjacent to any of the points on this graph, and therefore can be any of the 3 colors. And I'm also going to choose pink for this one as well. So we see here that the chromatic number is equal to 3, and therefore we're going to end up needing 3 different slots for exam.